1 volt and dropping. Don't need a charger, we need a tombstone.
Saw this APC, back UPS, ES550 in the e-waste pile at one of the places I did work for. Manager said I could have it since they like to be proactive about replacing worn-out equipment. It sat in a box at the apartment and through the move, but I found out the hard way that our new place here is much more susceptible to power outages. Label clearly says broken, so first step, verify the symptoms. No kaboom when I plug it in, and it is pulling a small amount of standby power. But when I press the go button, it screams at me, and the indicator flashes red. Manual says that means the battery's failed. Easy access to the battery compartment by flipping the unit over, pressing the latch tab, and sliding the cover off. This is a 12-volt sealed lead-acid type, typical for a small UPS. It's not meant to last long. In fact, most units of this type will only run for a few minutes at full load, enough to let equipment ride out short-term outages, or give time to save work and cleanly shut down. Smaller loads, such as a router, could get a couple hours of runtime. Gonna confirm diagnosis with my voltmeter. Just as expected, the battery's had it. But no sense in wasting money on a new one if something harder to repair has also failed. I'll put together some bits of 10-gauge wire with spade terminals, grab the jumper cables, and use an old car battery for the power source. My DC clamp meter will show the current if I can get it to behave. A quick tap before clamping on, just in case something in the unit decides to let the smoke out. No boom, so hook it up all the way, and time to see if it starts. Pulling a few more watts now when plugged in, and thankfully no signs of smoke. This model will always charge the battery when plugged in, regardless if switched on or off. Pressing the power button initiates a self-test. Sounds like a relay cycling, and the input power varies. Likely checking battery and inverter integrity before settling on a green status light. So far, so good. Now to test the inverter with a 40-watt incandescent light bulb as load. Transfer went smoothly, and the low voltage side looks good. Everything but the original battery checks out. On the surface, a simple case of order a new battery and move along. But that's not how things work around here. Recently lost a chunk of render progress to yet another unexplained blackout. No damage, and I finished the render later, but the insult alone got me thinking. I don't need 2-minute backup to let me save. I need time to finish what I'm doing, then shut down at my convenience. Unfortunately, that's in the realm of much beefier and more expensive UPS systems. Unless I simply attach a bigger battery. Caveat there is the inverter of these small units is designed assuming the battery will deplete before anything can overheat. Before I toss more parts of this project, I'll want to run some tests. Disassembly first to see what I'm up against. Use caution and disconnect all power sources before taking one of these units apart. Some types will have the inverter always active with parts energized with AC at all times, unless both mains and battery are unhooked. 4 little Phillips screws hold the bottom half of the enclosure together. Most of the interior volume is the battery compartment, with most of the rest taken up by a chunky transformer. Looks like built in mid-2010, so this unit's seen some use. Nice to see 130 degrees Celsius Class B insulation used on the transformer. As expected, a fairly dense PCB with control circuitry, battery charger, and inverter. Lots of surface mount components, and 2 layers to get everything crammed in there. Inverter uses a pair of IRF 2805 MOSFETs for switching in a push-pull topology. Heat sinks are simply chunks of aluminium for thermal mass, and that big transformer will similarly take a while to warm up. Should have plenty of capacity if I can keep it cool. On the transformer, the small plug carries the AC output from the secondary on the black and white wires, and the 12-volt connection to the board on the red wire. The larger separate black and white wires are the outer ends of the primary winding, and the large red wire to battery positive is the center tap. With the unit back together enough to power up, I'll connect 3 light bulbs adding up to 120 watts. This equals my computer at low load with 1 monitor running. While worn out, this car battery should still have decent reserve capacity. UPS datasheet claims 21.5 minutes at this output level, so I'll run it for half an hour and see what temps I get. Slightly warm, but nowhere near as bad as I expected. For reference, I repeat the test with the workbench shop light added, bringing the load up to about 210 watts, with a 120mm fan pointed at the electronics. Transformer got a little warmer, but the transistors stayed nice and cool. In this case, it's over 3 times the original rated runtime for this power level. Forced air cooling will do the trick. Now that there's proof of concept, time to make this a more practical device. For starters, the control board has no obvious provision for controlling the cooling fan. If I want the fan to only run when the inverter is going, I'll need to isolate a control signal that's only active in such conditions, or make my own. First thought was the transfer relay, but that coil is energized when the mains is live and off when the inverter is running. This would work as a source for the fan, however, turning the unit off would also turn the fan on if I use the relay as a signal source. Likewise, unplugging the unit would cause the fan to run and drain the battery flat. Inverter appears to be commanded directly by the microcontroller, not too keen on tapping in there. A temperature-controlled fan is an option, but might need input from both the MOSFET heatsinks and the transformer. Change of strategy time! The alarm buzzer sounds when the inverter is running and is conveniently a through-hole component. I'd want the option to tone it down since it does get annoying if running for a long time. Here's an opportunity to use its drive signal for fan control and add a volume knob at the same time. I'd want a hold circuit to keep the fan active during the pauses between beeps. A simple RC circuit driving a MOSFET is a good place to start. The double layer board made tracing the signal path a little bit tougher, but I found the buzzer circuit. 12-volt DC is supplied to the buzzer, with NPN transistor Q6 as a current sink, driven by signal BZDR. In this diagram, diode D22 prevents backfeed, and interestingly enough, resistor R44 seems to be on the ground side of Q6. Appears to be around 6 volts average dropped across the buzzer while it's sounding. This is where I made a bit of a mistake. I couldn't find consistent info on this particular buzzer. Many similar ones in this application are self-driving. The one on this board, as you'll see later, is driven by the microcontroller. Nevertheless, my second revision circuit idea also works in that case. Thus, we come to this layout. A potentiometer serves as volume control for the buzzer. When the buzzer circuit is activated, Q6 pulls the negative terminal of the pot low through D22 at the drive frequency, also drawing current through R3 from the base of QI. QI conducts, sourcing current through D1 and 1k ohm resistor R1, rapidly charging 100 microfarad C1 to battery voltage minus the diode drops. This drives the gate of MOSFET QM positive, which conducts and allows current to flow through the fan. When the buzzer drive signal stops, QI stops conducting and C1 begins to discharge through R2. A value of 560 k ohms equates to an RZ time constant of 56 seconds. The buzzer sounds in a pattern of 4 beeps every 30 seconds while battery is full, transitioning to rapid beeping every half second as the battery drains. Therefore, the fan will run whenever the inverter is active, but turn off soon after the buzzer stops and won't run in other situations. Since there won't be anything in the battery compartment anymore, this is a perfect place to mount the cooling fan and the additional electronics. 120mm fans don't quite fit, and these ones I have don't develop much static pressure. I got a higher speed 80mm fan when I ordered the parts. Had to modify the battery door and tracks to let it fit, no longer a big deal since there's no more heavy battery in there. Once it's all measured out, this 3-inch hole saw punches through. Got the screw holes to line up, and a piece of hardware cloth to be a fan guard. Transformer and power stage of the inverter are both conveniently located at this end of the enclosure. A bunch of 3/8-inch holes will let the air through. Don't need as much structure without the battery. There's air blast for the components. Now time for exhaust holes. This is also a balance between enough holes to not choke the airflow, and leaving enough structure so that the enclosure doesn't crumble. ABS is pretty forgiving to work with, but beware spicy fumes when it gets hot, and the freshly exposed plastic will off-gas for a while. Strategically breaking out these ribs in the transformer supports will also allow air to circulate around the core. A few little exhaust holes on the back side of the inverter board will encourage circulation behind the inverter section. Additional components have arrived, so time for extended duration test. 215 watts for an hour, 7 times the stock endurance. Wedged a thermocouple in one of the heat sinks, and another in the transformer primary coil. Transformer sensor slipped a bit after I put the housing together, so actual temps at peak were a bit warmer. Tried to get some shots of the transformer with my IR camera through the exhaust holes. While that runs on fast forward, I'll put the circuit board together through the magic of editing. My soldering skills and soldering iron were both a bit rusty, but I think I fell back into a rhythm. This pack of mini prototyping boards I got a while ago came in handy, perfect size for the little fan driver. Even after triple checking my work, I'm quite cautious about letting the smoke out. I did think ahead to get enough components to build a second one in case I made a mistake. A pair of 470 ohm, 5 watt resistors in parallel will be current limiting insurance in case I messed up. It passes the no load test and voltages look good. Triggering the PNP input stage by pulling the white wire to ground charges the timing cap just as expected. Hooking up a fan as load, everything looks good, so hooked to full voltage without the resistors for a second round of testing. The MOSFET performs better than expected in terms of gate threshold, holding the fan on longer without even a hint of warming up as it tapers off. Getting this camera angle was tough, but I extracted the buzzer from the PCB. Wired up the pot for volume control. And got the buzzer situated on the same board as the fan driver. During testing, here's where I found out the buzzer must be AC driven and is not self-driving like similar parts I researched. Either way, my circuit will still work. Putting crimp spade connectors so the fan driver can be unhooked easily. And prepping these 8-gauge supply wires. Had to trim a few strands to fit the connectors. 10-gauge of wire would be suitable here, but I'm upsizing a bit on purpose. Every fraction of a volt dropped will eat into the inverter's efficiency and its runtime. Terminals on the UPS are slightly loose as well, so those get swapped. Signal wires get spade terminals as well. Volume pot will exit the housing through the top of the old battery compartment. A quick measurement and a 1/4 inch hole, bumped up to 5/16 for easy fitment. At first, I've been indecisive about where I get ground for the fan driver. Had to choose at this point, so tapped off the negative terminal of this capacitor on the low voltage side. Routed that wire out alongside the red and yellow. Fan gets spades too. Everybody gets spades in the quite likely case I need to pull this thing apart again. Battery cables will exit the rear through these notches in the cover. Had to correct a few issues with the spade type matching. Then hot glued the driver board. A little wrangling, but the cover locks in place without any wires jamming the fan. Picked up a group size 27, 12 volt, marine deep cycle battery. While not too much bigger than the H6 battery I was using for testing, this has a reserve capacity of 180 minutes. This equates to a 75 amp hour capacity at a 25 amp load. The fuses on the PCB will protect the inverter, while this 80 amp bolt-on cartridge will protect the cables. Unlike the mini battery that came with the UPS, this big one can output hundreds of amps for long enough to liquefy the cables. I'm not taking that chance. Here I'm tightening just enough for testing. We'll torque down at final assembly. Tap test to check for excess current, a major fault which spark and or pop the fuse. Once again, not final assembly, just enough to confirm operation. Alarm sounds when I power it up in battery mode, and the fan spools up. Then, a couple minutes after I turn it off, the timing capacitor discharges, and the fan shuts off again. Volume control lets me tone down or mute the alarm as well. All according to plan. Moving on to the battery box. There are fancy ones out there with lots of accessories, but I can get similar features for half the price by combining with a separate kit. This one has a switch, a voltmeter, a 12-volt socket, and a USB charger. The mounting plate doesn't quite fit anywhere on the box lid, so I'll install each module separately. Modules have a diameter of about 1 inch, so a 1 1/8 inch hole was perfect. A step drill would have been slightly easier to use compared to these paddle bits meant for wood. They still got the job done. Deburr the holes. Get the first pair in. And repeat for the second pair. Each has a lock ring to hold it in place. Modules are too far apart, and I wanted to change up how they're wired so the voltmeter is always connected, so I gotta build a new wire harness anyways. Voltmeter only pulls 8.5 milliamps, so no problem for a battery that will always be on float charge. An inline 20-amp automotive fuse will keep this set of items safe, with 3/8-inch ring terminals to hook to the battery. Noticed a lot of air escaping around where the fan mounts, and the latch for the door. Duct sealant works nicely here, and is easily removable later if I need to replace the fan. Wires will go out these notches in the back, and down through half-inch holes in the battery box lid. Because the UPS will need to be removable for service, 3M dual lock is a good choice to hold it down. Slight struggle to get the ring terminals through. 9/16-inch holes would have been better if I had a bit in that size. Extra armor on the cables can't hurt either, though I've confirmed the holes have been well deburred. Washers and proper torque on the connections for final assembly. Inverter powers up. Voltmeter is running constantly, and turning on the switch powers up 12-volt socket and the USB ports. After being plugged in for several hours, the battery settles on a float charge of 13.5 volts, and input power to the UPS drops to just a couple watts. Perfectly safe to leave connected long term. One final test for good measure with a 75 watt light bulb and the 80 watt shop light. All systems working as intended. Time to install. Cable management will need some work, but that's an issue for another day and future me. Before anyone calls it out, yes, daisy chaining power strips is generally a bad idea. In this case, the loads are well defined and well within the limits of the circuits, and the first power strip also has much higher surge rating than the UPS. First test is with the PC idling in the BIOS menu to prevent any corruption. Lamp flickers on transfer, but PC doesn't even notice. Second test is a more realistic load. I've booted into Windows, got the Portable Sound Booth Part 2 video playing on YouTube, and a few other apps running behind for a moderate load. Once more, doesn't notice the power cut and keeps chugging along. I'm now insulated against surprise outages, with several hours of backup power for other small household items as well. Thanks for joining me on this project, I really appreciate your support. There's more on the way, links in the description, and I hope to see you around soon. Until next time.